Mark his corner. Mark his corner. Woo! You got a whopping 95 on this exam.
95.
Nice, dude.
Yi Shun Zhao. Yi Shun Zhao. Yuan Yang Zhang. Yuan Yang Zhang. Good name too. Good. Jia Shi. Mozin Okari. Brendan Cook. Andrew Curtis. Thanks. Chua Fung. Guanan Guo. Gao Liu Qing Gao.
Square away, but I think it might be
Na Yong Li.
T overall and minus T overall.
Shu Ting Li.
There's no comma.
Shu Ting Li. Xiao Shu Li. Xiao Shu Liu. Okay. The rest of you, I can have maybe Aditya read aloud the name, and then you can take more up.
Who's Karmani Agarwal? Karmani Agarwal? Johnson Agarwal? Jake, right? Who's Jake, right? Uiuc.
I was Googling it and it was not.
Who is Gene Buell? Ben Cheslow? Ethan Chen? Eugene Wade? Timothy Lawson? Eric Delanoy? Jason?
Okay, here are the statistics on exam. I think the exam is a little bit on the long side, so it's hard to finish it. So let me go through the exam review. And let me start with problem 3, my problem. Okay, problem that I'm giving. Because I don't think I can finish all the 4 problems here.
Cody Kyo? Who's Cody Kyo?
Problem 3. Okay, let's start now and see how long it takes to. And then you're given that impulse response is given by this thing over here. Find h of omega. Okay?
Alexander.
So that is most easily done by direct integration. This thing looks something like the direct of e minus 1 over 2. This is 2. This is
James Howard.
0 is 1. Because something looks something like that. So this needs to be taken from 0 to 2. E to the minus t, e to the minus j omega t dt. Okay, integrate this, and if everything turns out to be correct, then we get 1 minus e to the 1 plus j omega 2 over 1 plus j omega. Okay, I won't go through the detail, but this is the way to do it. But there's another way of doing that, which is somewhat unusual, which is to notice that t minus 1 over 2 Fourier transform to sing of
Kyle Wilson. Robert Masson.
of
Robert Masson.
omega e to the minus j omega. Okay, one thing is to notice that this thing Fourier transform to that thing, and then if you were to just add the phase shift. This is not a phase shift, but it's an exponential factor. It corresponds to doing a complex frequency shift. So if you do a complex frequency shift on this, you get something like omega minus j to the minus j omega minus j. Okay, because this thing, we know how to do this thing when we have j omega naught t. This will do a frequency shift, but what we have now is actually minus t. Okay, so j omega naught is omega naught is actually equal to j in this case. If omega naught is taken to be j, you get this frequency shift. So if you do a complex frequency shift, you get the right answer too. Okay? Let's do problem 2. Problem 2 is a little bit complicated. They ask that ft is equal to 2 rec t over 2. So we find the output yt with the convolution of ft convolving with ht. Okay? And this rec t will look something like this. 1 minus 1 and then 2. So you have 2 rec t over 2 will look something like this. And then you have to convolve with something that looks like that. So you need to flip over. And there are 2 cases to consider, because we will flip this over. Then you can write y of t as being equal to 2 rec of tau over 2 rec of t minus tau minus 1 2 minus t plus tau. Okay, you just do this, and then what you need to do is actually flip this function over. Flip this function over. There will be 2 cases. One where this function is over here. Okay, this t minus 2. And then there will be another case where this function is over here. t minus 2. This is 1, this is minus 1. Okay. So you have to do these 2 cases separately. Figure out the overlapping integral separately. And then you get 2 cases. When t is less than 1, is less than minus 1, which is this case over here. T is less than 1, is larger than minus 1, you do this integral. Okay, then you have yt being equal to minus 1 to t, minus 1 to t, which is this integration over here. And then 2e to the t minus tau d tau, which gives you something like 2, 1 minus e to the minus 1 plus t. Okay? And then the other case is this case over here, when t is larger than 1, t minus 2 is less than 1. Okay? So this is t larger than 1, t minus 2 less than 1, so t is in this range, then you have yt being equal to t minus 2 is the starting point of this. Okay? 1, 2 e to the tau minus t d tau. And for this, you get this little answer, 1 minus t minus e to the minus 2. And then 0 otherwise. Okay? So this is part 2. Part 3, there is an error. In the exam, I will give 3 points back if I give you 0 points for this. Okay, this should be ft equals to 1 over a rect of t over a. Okay? So when a tends to 0, so this is wrong, this is right. When a tends to 0, f of t tends to the delta function. So y of t just is equal to h of t for this thing. And because I make this mistake, and I'm willing to give 3 points back if I take off points from this problem, okay? You can come to me and ask for 3 points if I grade you wrong. Okay? So part B is a whole bunch of convolutions. Problem 3b. Okay, 3b, you're given that R3 is equal to delta t convolving with cosine of omega ct. Okay, so delta t is a triangle function in Fourier transform to sin squared of omega over 4. Okay. Cosine omega ct Fourier transform to pi delta omega minus omega c plus delta omega plus omega c. Okay, then r of omega, okay, will just be equal to this convolving with that. And if you convolve this with that, you get 1/4 this divided by 1 over 2 pi. You convolve and divided by 1 over 2 pi because if you apply the formula correctly, then this should be the answer. Okay, this is part B, number 1, part 1, part 2. You are asked to find GT, which is RT, to be modulated by cosine of omega naught t. The omega naught is larger than omega c. Okay, so what you have then is that G omega will be R of omega, which is this function convolving with this new delta function. But there is a division by 1 over 2 pi, so you have 1 over 2 left. Delta omega minus omega naught plus delta omega plus omega naught. And then when you convolve this with that, you get 8 terms. Okay? You get 4 terms, sorry. You have 1 over 8 sin squared omega minus omega naught c over 4. And then plus beta with omega minus omega naught plus omega c over 4. And then you have another term, this is sin squared. Okay, sin squared omega plus omega naught minus omega c over 4 plus sin squared omega plus omega naught plus omega c over 4. So you get these 4 terms. Okay, the next one you're asked to sketch. When you sketch this, then you have four terms. Okay, you have one that looks something like this, another one that looks something like this, another one that looks something like this. You get 4 of this. They all have the same peak. The peak in 1 over 8, and then the center frequencies minus omega naught plus omega c, omega naught plus omega c, omega naught minus omega c, sorry, omega naught plus omega c, and then minus omega naught minus omega c. Okay, so this is problem 3. Let's try to do problem 4. Okay, let's see if we can do all the 4 problems. Problem 4 is about some echo experiment. Problem 4, part A, number 1, you're given that yt is equal to ft plus ft minus 2. Okay, so this is equal to ft convolving with ht. So what impulse response should you have to get this kind of result? So it's quite obvious that the impulse response must just be that. Okay, there's part 1, part 2. Is this system Bible stable? Okay, we learned in the textbook that an impulse response that as a direct delta function is Bible stable. So the answer is that it's Bible stable. Okay? And then if ft is bounded, because if ft is bounded, then yt is bounded. It's always bounded, okay? So number 3, ft is equal to cosine of omega of pi t over 2. Okay? So if we find what h of omega is, h of omega from this thing, okay, will just be equal to 1 plus e to the minus j2 omega. Okay, if you Fourier transform this, you get h of omega to be this. Okay? Then if this is your f of t, you can find its Fourier transform. Fourier transform will be pi delta omega minus pi over 2 plus delta omega plus pi over 2. Okay? And then y of omega will be equal to f of omega times h of omega, okay, which is over there. And then when you multiply them together, and then using the shifting property, the sampling property of the delta function, you will get this to be pi delta omega minus pi over 2. With this function being evaluated at omega equals pi over 2, so h pi over 2, and then plus the other term, which is omega plus pi over 2, with h evaluated at pi over 2. Okay, the trick about this is that when omega equals pi over 2, this is just e to the minus j pi. So this becomes minus 1, this becomes 1, minus 1, and this becomes 0. So all these terms become 0. Okay? So all these terms become 0, and your answer is 0. Y omega is 0. Okay, part B, let's see how we tackle part B. Part B, you have f of t is equal to 2 sin squared 2t, going to a diagram, multiplying with the sampling functions, the impulse train, delta t minus n pi over 2 being the impulse train, and then s of t is the signal that's been sampled, and then it goes through a low-pass filter function that looks something like this, minus 4 to 4, and then h of omega. You're asked to find what y of t is. Okay, you're given that f of omega should look something like this because it's a Fourier transform of distinct function. Okay, so it has a peak of pi, 4 minus 4. Okay, and f of omega looks something like that. Okay, so you ask if this thing is undersampled. You ask if this thing is undersampled. Well, the sampling frequency omega naught, or this should be t, okay? T is equal to pi over 2. The sampling frequency is equal to 2 pi over t, is 2 pi divided by times 2, which is equal to 4. So the sampling frequency is equal to 4, but the bandwidth, okay, the bandwidth is also equal to 4, but Nyquist's sampling theorem says that this must be 2 times the bandwidth. Okay, 2 times the bandwidth, but the bandwidth of this is 4, so this must be 8. And the sampling is at 4, so it's undersampled. Okay, so the answer to part B, one is undersampled. It does not satisfy Nyquist's sampling rate. Part 2, sketch S of omega on the real axis. Okay, because this impulse train is undersampling, there will be overlaps. When you multiply them with that, you get an overlap S of omega. The fundamental one will look something like this. It's 4 minus 4. and then with an amplitude of 2. Okay? With an amplitude of 2 because of the sampling theorem, if you go through the proper formula. But then there will be overlaps.
Professor Chu,
Yes?
is the bandwidth 4 or 8?
What is that?
Bandwidth.
No, the bandwidth is 4, but 2 times 4 equal to 8.
It's 8, right? Minus 4 to 4.
No, the bandwidth is defined to be this.
Yeah.
Okay? 4. Okay? So because of the undersampling, the spectrum looks something like this. There are a lot of overlaps. Okay, but if you try to pass this to the band pass or the low pass filter, you pick up this part of the signal. Okay? This part of the signal turns out to be the sum of this one and that one. It turns out to be a constant. Turns out to be a constant. So you picked up a constant spectrum. Okay? Y of omega actually would look something like this. 2 and then minus 4 to 4. Because of the aliasing effect, these triangles overlap with each other. Y of omega looks something like that. Okay, after you pass through the bandpass filter. And then if you were to look for the Fourier inverse transform of this, okay, Y of omega is equal to 2 rect of omega over 8, which means that Y of t is equal to 8 over pi sin of 4t. Okay? So this is problem 3 and 4. Let's get back to problem 1. Problem 1. Are there any questions so far? Let's go to problem 1. Problem 1 is on the long side, I think. Okay, maybe we do problem 2 first. I think problem 2 doesn't look that long. Okay, let's leave problem 1 to the end. Okay, let's do problem 2. Problem 2, you're given f of t, and f of omega is given to be something that looks like that. And then it has a peak of 2 pi, and then it goes to 1, it goes to minus 1 over here. And hence you can say that this line is 2 pi 1 minus omega. This other line is 2 pi 1 plus omega. Okay, so f of omega looks something like this. It asks to find the energy. Part A, find energy in this signal. You can use Pascal's theorem and then just integrate off of f of omega squared d omega. Okay, you perform this integration. And if you perform this integration, you need to only do from 0 to 1. Okay, and do it 2 times, so you get a 2 times 2 pi 0 to 1, 2 pi square, 1 minus omega square, d omega. Okay, and then you get 1 over pi, and then there's a 2 pi there, and then 4 pi square, 4 pi. I guess you get 4 pi in total. And then this one you get 1 minus omega cube over 3. Omega cube over 3, 0 to 1. Integrate this with respect to omega, you get omega cube divided by 3. Okay, set omega is equal to 1 and 0, set omega to 0 is 1/3. So the answer is 4 pi over 3. Okay? 4 pi over 3 joules. Then part B. Part B, find its 3 dB bandwidth. So 3 dB bandwidth is defined to be f omega over f of 0 to be equal to 1 over root 2. Okay, you look at this function, find where the value diminishes to 1 over root 2 because it's half power bandwidth. 1 over square root 2 voltage bandwidth. Okay, so if you square this, this becomes 1 over 2. When you square this, this will become the ratio of power But if you don't square it, you should put the 1 over root 2 over there. So you work out this function, okay, 2 pi, 1 minus omega over 2 pi. This is the value at omega. Let's say that this is omega, where is the half power bandwidth. And then you want this to be 1 over root 2. This implies that omega is 1 minus 1 over root 2. Okay, you get that to be your answer. And then part C is if this signal goes through the following system, we modulate it twice at f of t, and then first time modulating by cosine of 5t, second time modulated by cosine of 2t. Okay, you get m1t, m2t. And then you pass it through a bandpass filter, okay, h of omega. Then you do an envelope detection in one branch, envelope detection, and then the other one you just let it be free. So you're asked to find what the two answers are, y1t and y2t. And then the bandpass filter looks something like this. H of omega has a 1 and then has a bandpass here, another bandpass here, and then 2, 4, minus 2 minus 4 omega. Okay? So the first modulation, there's a little bit of problem with the solution. M1 of omega. M1 of omega is equal to f of omega convolving with pi, convolving with half delta omega minus omega c plus omega delta omega plus omega c. Okay? So this is the first convolution, the first multiplication corresponds to convolution. So this gives you half f of omega minus omega c. Omega c is 5. Okay, omega c is 5 in the first case. So it gives you this one plus half of f of omega plus 5. Okay? So sketch m1 of omega. Part 1, sketch this thing. If you sketch this thing, it should look something like this. Centered about 5 minus 5, and then it should be 6, 4. So this one gets shifted over that way, and then the other one gets shifted minus 4, minus 6. So you have this peak. And then there is a peak of pi. Okay, there's a 2 pi divided by 2, this peak is pi. So this one is m1 of omega. Okay, part 1. Part 2, sketch m2 of omega. m2 of omega is just m1 of omega convolved with another delta function again. Okay, so you need to convolve this, which is this one, again, with this thing over here. Okay, so m2 of omega is m1 of omega convolving with half delta omega minus 2 plus delta omega plus 2. Okay, you take this picture and convolve with that delta sequence, and out comes this m2 of omega. Okay, you have 3, you have 7, minus 3, minus 7. You have this triangle function being peak over here, triangle function being peak over here, triangle function being peak over here, triangle function being peak over here. This was pi, and then there's a factor of 2 again, so it's pi over 2. Okay, so this is pi over 2. Okay? And then you're going to pass through this band pass filter. This is 4. This is 2. This is minus 2, minus 4. So this band pass filter will pick up these two things. Okay, we'll pick up that 2 thing. So after that, after the band pass filtering, what happens is that over here you will have y2 of t. Okay, so y2 of omega will just have these 2 thing over there. Okay, so this is pi over 2. This is y2 of omega and how it looks like. And this is just equal to this thing convolving with 2 cosine or 2 delta functions. So y2 of t, okay, y2 of t would just be equal to half sin square t over 2, which is this function over here. Okay, this thing Fourier transform back to a sin function, okay, times cosine of 3t. Okay, because this is 3, this is minus 3. Okay, so y2 of t should look something like that. If you Fourier transform this back, you should get sin square t over 2. Okay? The factor of half comes about because there's a factor of half every time when you go through a band pass filter. y1 of t is the one that went through the envelope detection. So y1 of t should just look like half sin square t over 2. Okay, the envelope detection removes this thing. Okay? Are there any questions regarding this? So I think we're done with problem 2, right? Let's go to problem 1, which is the longer problem, I think. No questions about this, we go to problem 1, okay? Problem 1. Problem 1, part A, you're given that f of t is given by a Fourier series extension n odd, okay, 1 over n pi cosine of n pi over 6t minus pi over 2. And you're given more explicitly that this is just 2 square functions. 1/4 when t is between 0 and 6, minus 1/4 when t is between 6 and 12. Okay? So if you were to sketch this, the capital T, the period is 12 seconds. So if you were to sketch f of t as a periodic function, it will look something like this. 6, 12, t, 1/4 minus 1/4. Okay? So you're first asked to find the power, the average power of f, part 1. Average power of f, the signal f is just 1 over t integration over the period of ft squared dt. Okay? You can see that it consists of 1/4 square plus another 1/4 square, and then the t is 12 seconds, so you put 1 over 12, and then you need to have 1/16 plus 1/16 integrated 2 times, that will give you that thing, But then each one of them has to be multiplied by 6. Okay, so you have to multiply by 6 over here. 6 times 1/16. So you get 12 over 12, and the total answer is 1 over 12, or 1 over 16 watts. Okay, that's part 1. Part 2, you have to pass this thing through a bandpass filter. The bandpass filter looks something like this. This is pi over 3 pi omega minus pi over 3 minus pi. So when it passes through the bandpass filter, it's going to only pick up 2 harmonics from here. You can actually work out the harmonics, and then you're given that the bandpass filter has a phase that is given by this plot over here. It has a value of 1/4 at minus pi, the value of minus 1/4 at pi. Okay, this is the phase function. So you first try to sort out what Fourier harmonics would go through. Okay, so you try to look at the Fourier harmonics. You make a table. N is equal to odd, then n can be 1, 3, 5, 7, 1, 3, 5, 7. Okay, then n omega naught is equal to pi over 6 in this picture. Okay, omega naught is pi over 6. So you have pi over 6 for the first one. You have 3 pi over 6 for the second one, 5 pi over 6 for the third one, and then 7 pi over 6. Okay? And if you compare with the bandpass filter that passes signals between pi over 3 and pi, only these two harmonics will pass through. The other harmonics are stopped.